it has come to this. I am here at my home under self-quarantine from the coronavirus, and classes have been canceled. However, I still need to deliver the material to you, so bear with me. This is the first kind of time I've ever recorded myself, I think, period. So it's going to be cringy. I'm going to make mistakes. We're just going to have to push through it. So, for example, the microphone's bad. Hopefully you can hear me. Might not be that big of a deal. In the future, I'd like to get a better microphone, but this is what we have to work with. This is my basement. I spent a couple hours getting this set up in this like a makeshift lecture hall, but there's not a lot of room. So you'll see like I'll be moving across here. I'll be writing. I'm going to be covering up parts of the board. Deal with it, I guess. I'm doing my best. We'll figure it out. And as things progress, hopefully I get a little bit better at it as we go. So if you're joining me from not my class, this is CSC363 at the University of Toronto. You're jumping right into the middle of the course, but it's basically complexity and computation, theory of complexity and computation. And what we saw last time was we can actually begin to break problems into certain classes. And we saw two classes of problems. We saw P and we saw NP. So right off the bat, maybe I'm standing in the way. Like I said, we'll have to deal with it. So remember, P was the class of all problems that had polynomial time deciders. So we can decide these problems or languages in polynomial time. NP, well, that one was a little trickier to define. NP in general, very informally, if you want the formal definition, check your notes from last week. But the informal definition is, in general, they can be hard to solve, but they're easy to verify. Meaning if someone gives you a problem, it might be hard to solve that problem, but if they give you a solution to that problem, you can verify it or determine if that's a correct solution or not in polynomial time. Okay, so what does that mean? Well, we saw some specific examples last time. We're going to see some more specific examples today because we have these classes of problems, and what's the main goal here? Why do we separate into these classes? Well, we want to order these problems. We want to say this problem's harder than this problem's harder than this problem, and we're going to call this problem over here the hardest. We want to build some kind of hierarchy, a relation between languages. And the way that we order languages or build this hierarchy is with a natural ordering, like less than or equal is. And as we saw last time, we have something called polynomial time reductions. So we can take a problem A, write something like this, meaning A, polynomial time reduces to B, and that's the ordering we're going to make. So what does that mean exactly? A, polynomial time reduces to B? Well, you can check the formal definition of your notes. It's not as bad as the computational reductions, the mapping reductions. The way that we're going to think about it is if you have a black box that solves problem B, and we assume that you can call that black box on instances of problem B, run it in constant time. If you have that magical black box available to you, and you can then come up with an algorithm that solves problem A in polynomial time, given access to that black box, then we say A, polynomial time reduces to B. And as far as complexity goes, this means that basically our interpretation is B is at least as hard as a problem than A is. So A we consider the easier problem or potentially easier problem. B is at least as hard to solve as A. And that starts to build our hierarchy. So what are we going to do today? We're going to take a look at a few more NP problems, 3 specifically. Now, you know what? Let's take a break right here. When I'm uploading these things, again, I've never uploaded anything in my life. So we'll see how it goes. I'll probably take our typical 2-hour lecture and break it into smaller sections. So, I mean, we'll play it by ear. You'll have to, cope with it, bear with me here. But in general, I think the material is going to be shorter because as you know in lecture, we have those breaks and whatnot. I might just say, okay, pause the video here, take a crack at this problem, and you can kind of treat that as your breaks, or you can just ignore it and can continue on with the lecture. That's your call. But in general, I think, we'll spend less time on it than in lecture, and I might upload in like 30-minute segments. Who knows? We'll see. So, what's the first problem we're going to see in this, today's lecture, whatever you want to call it? Well, there's a graphing problem called the vertex cover problem. And if you took CSC363 with me, we actually looked at this vertex cover problem. So what is this? Well, given a graph, and yes, I'm probably covering, whatever. Given a graph, and what's a graph? A graph is just a set of vertices and a set of edges. Given a graph G equals VE, a vertex cover, and I'm lazy, I don't want to write vertex cover, and these whiteboards, they aren't the biggest, so I'm just going to write VC for vertex cover. A vertex cover, and we'll call it C, is a subset of V such that, so C meaning it's a subset of V means a vertex cover is just a set of vertices. So C is a subset of V such that for all edges, I'll call it V1, V2. Remember, what's an edge? Edge is just like a two-tuple of two vertices, the source node and the target node. So V1, V2, for every edge in E, V1, V2, V1 is an element of C, or V2 is an element of C. So what is a vertex cover? That's the formal definition. My experience is it's just easier to do a couple examples. Basically what it means is we're trying to find a set of vertices which cover all the edges in the graph. Now I think like students have this kind of weird intuition based off the name vertex cover. They think it should be called edge cover because it's covering all the edges. And you know, I actually get that, but it's just something you're gonna have to get over. There's an edge cover problem, and I, as well as you, may think it should be called the vertex cover problem. But anyways, that's a side note. Like, it's hard, you know, I'm gonna run off on these tangents without having you guys here. It's hard to, you know, kind of play off the class, but it's definitely awkward for me. Let's continue. So let's do an example. So let's do a graph. Let's not go too crazy. 4 nodes. And we'll hook these suckers up. Something like this. And let's put an arbitrary labeling on these guys. Okay. So what's a potential vertex cover of this graph and what isn't? Well, let's throw a couple candidates up on the board. C1. I'm just going to let C1 equal V, meaning I'm just going to let it equal 1, 2, 3, 4, 5, 6. C2, empty set. C3, let's see, 4, 6, and 1. Yeah. C4, let's do a 4, 6, and 2. See, there's our 4 candidates. I want you to take a moment, pause the video, and see if you can figure out, I guess I did the pause at the wrong time, no worries, and figure out which one of these things is a vertex cover and which is not. So take a moment, look at that one, look at this formal definition over here. You know, maybe fight your intuition a little bit, depending on your intuition, it might be wrong. Look at this formal definition, what one's a vertex cover and what's not. So take a moment, pause the video, and we'll take it up. Okay, so this is a little bit easier than in class because I can kind of just assume you've taken 5 minutes to look at this and you understand what's going on, you Wikipedia what a vertex cover is, etc. So, is this a vertex cover? 1, 2, 3, 4, 5, 6. Is V a vertex cover? Yeah, it is. Why? Well, you take any edge. Take this edge. Is 1 or 2 in this potential vertex cover? Yeah, of course, is 1 and 2. It doesn't say that 1 and 2 can't be in there. It just has to be 1 or 2 is in there. Take this edge. Is it covered? Yes, 2 and 3. Take this edge. Take any edge. It's all covered. This one is good to go. That's a vertex cover. Is the empty set a vertex cover? Nah, it's not. While you take any edge, take your pick, whatever one, it's not covered. Neither its source nor its target is in the empty set. Therefore, the empty set is not a vertex cover. What about this one? Well, we'll take a couple edges. Is 4, 6 covered? Yeah, it is. Is 5, well, I should say it is not 4, 6. Is 4, 5 covered? Yeah, it is, because 4 is in our candidate C3 vertex cover. 5 isn't, but that's okay. We just need one of 4 or 5 to be in there. What about this edge? 5, 6? Yeah, it is. 6 is in there. What about this this one? 2, 5? Is that in there? No. So this one is not a vertex cover. And in fact, there's one more edge that violates it. So 2, 5 and 2, 3, neither of those edges are covered. Okay. Well, what about 4, 6, 2? Is that a vertex cover? Well, this one's still covered, this one's still covered. 3, 5, that's not covered. So that one isn't. So none of those are vertex covers. And what I'm going to have you guys do now is see if you can come up with the smallest possible vertex cover for this particular graph. Take a moment, look at it. Does there exist a vertex cover of size 3, size 4, 5, 2, 1? Okay, and we're back. Well, what can we do? Let's see. I'm looking, there's a lot of edges connected to 5. I'm going to go with 5. See what happens when I add 5. So that takes care of this edge, this edge, this edge, this one. I still got 2 remaining. So for instance, 5, 1, 3, would that be a vertex cover? Yeah, it would. Covers this edge, covers this edge. Is that the best possible vertex cover in town? And I throw around that word best. What does best mean? I want the smallest possible vertex cover. So the one advantage of having my own little mini lecture hall is I get to supply the erasers. Shout out to the Monday section there. Make sure everything's stocked up. But I can do something better here. What's going on? What if I add 2? 5, 2. Is everything covered? I hope it is, or otherwise I screwed up the example, which is possible. So this one's covered, this one's covered, this one's covered, this one's covered, that's covered, that's covered. Boom! Vertex cover. Is that the best possible vertex cover I can do in this graph? Turns out it is. And I mean, you should be able to convince yourself that that's true pretty quickly by inspection. In order to beat that one, I'd have to have a vertex cover of size 1, which would be quite difficult. But this is the best we can do. But even for a 6-node graph that's pretty simple, I mean, it's easy to come up with this answer, but it's not like you can just glance at the graph. Good, I got it, no problem. So you can imagine how a human mind wouldn't be able to cope with a problem like this if we dialed up to 10 nodes. It'd even be tricky. You might given an hour though, you might be able to solve it. Or maybe you're a genius, maybe you can do it in a couple minutes. I don't think I could. What if you dial up to like 100, 1,000, a billion? It's hopeless at that point, really, for a general graph, trying to find the smallest possible vertex cover. The set, or a set, of vertices that cover all the edges with the fewest number of vertices possible. Okay, so we need a computer, we need an algorithm to solve this problem for us. So let's come up with one. I mean, there's some things you might be able to try, like take vertices that have, a large degree, meaning large number of edges pointing to them. That's a good idea. It turns out you can come up with counterexamples to that. So let's take a step back. What if we just brute force this sucker here? If we brute forced it, how many potential vertex covers are there given a general set of vertices? So if the magnitude of V equals n, on what order? How many subsets? How many potential vertex covers are there? Well, you get that typical subset cardinality thing. And basically, you get a choice of 2 for every vertice. So you take a vertice 6, do I include it, exclude it, include, exclude, include, exclude, make that choice n times, and you end up getting something on the order of 2 to the n. Potential vertex covers. So brute forcing, it's exponential. Well, bad news for you, or maybe not bad news for you, but bad news for people that want to solve the vertex cover problem. That's the best, really, that we know right now. To find the optimal solution every time, brute force is the best we can do. Well, that kind of sucks. But let's think. This vertex cover problem, let's try to write it out as a language. Remember we talked about before, languages are essentially problems, and problems are essentially languages. Let's try this. Let's try to write this as a language. So it's going to take in a graph, and you're saying, Vince, you're in the way. Yeah, I know. So this is going to be the set of all graphs in some number k, such that there exists a vertex cover in G. This thing's swinging. This wall's not straight. A vertex cover in G of size k or less. So for instance, if I were to give it this graph and the number 4, that would be in this language, because there exists a vertex cover in this particular graph of size 4 or less. But now you can see how in this language form, we can kind of exploit this number here and iterate through and ask it maybe a polynomial number of questions, and you can determine what the lowest value of k is. In fact, you could even do a binary search. But for instance, for this one, you could ask, does there exist a vertex cover of size 6? Yes. 5? Yes. 3? Yeah. And I'm pointing to the nodes. I shouldn't be doing it. Does there exist a size 6? Yes. 5? Yes. 4? Yes. 3? Yes. 2? Yes. 1? No. Therefore, the smallest possible vertex cover is of size 2. So this language, what class of problem is it? Is it P or is it NP? Well, is it in P? In order for it to be in P, I need to be able to decide this thing in polynomial time. Well, I don't know if that can be done, but I know I don't know a way to do it. Maybe it's in P, maybe it's not. What do we need to know or be able to determine if it's in NP? Well, think of it this way. It's hard to come up with, what's the smallest possible vertex cover, or coming up with a vertex cover of size k or less in general can be difficult. But what if someone gave you a potential vertex cover, C, and they said this is a vertex cover in G of size k or less? You say, okay, well, how would I verify that? Is that easy to verify? Yeah, it's not too bad to verify at all, actually. All you have to go through is check every single edge in G. Is this edge covered? Well, you check that potential solution they gave you. Okay, yeah, this one's covered, this one's covered, this one's covered. They're all covered, and then you have to check, of course, if the size of the potential candidate set they gave you is less than or equal to k, but if it is, then that's a potential solution. You can also verify if it's an incorrect solution. You just go through all the edges. No, this edge isn't covered, therefore it's not a vertex cover. And in fact, that's what we were doing over here. We were verifying if these were vertex covers or not. We weren't necessarily coming up with the vertex cover yet. We were just verifying the correctness of these things over here. So that's the vertex cover problem. It's an important problem, lots of applications. Imagine graphing problems in general have applications, but you have a network like this, and it's like, what's the fewest number of nodes in this network I need to cover everything? Maybe I need to upload, some information, and I want to just upload it to the fewest number of machines so it'll propagate, 1 degree away, things like that. Or topically, if the graph is, connection of human interactions, and you want to know what's the fewest number of people to get some kind of coronavirus required for everyone to be infected, you know, you can find that number, maybe it's like 20 or something, and you can go on news, say, it just takes 20 people to be infected for everyone to be infected. And then people freak out and shut down the university. But, I mean, there's countless applications to these types of things. So that's the vertex cover problem. That's problem number 1. And we know, based off that discussion we just had, and I use the word discussion lightly, especially since you're not here, it's an NP. I don't know if it's NP or not. I'll say this, if it's NP, P equals NP. But it's definitely in NP. Well, remember, I want to start ordering. I want to start building a hierarchy of problems in NP. Okay. So that means I need to come up with another problem to potentially compare vertex cover to. What problem is that going to be? I wonder what that sounds like on the video. It might be awful. Blame the university, not me. Okay. The second problem I want to look at is independent set. The independent set problem is also a graphing problem. So, given a graph, G equals V, that's what a graph is. I'll call it I is, again, it's going to be a subset of V. So I, again, is just a set of vertices. An independent set is just a set of vertices. Is an independent set if for all the vertices in I, for all V1, V2 that are in I, so take any two vertices in I. We say, and again, I'm trying to orient myself here. For all vertices V1, V2 in I, what is it? Yes. V1, V2 is not in E. Okay. What does that mean? Well, this one's actually, I'd say, easier to conceptualize than the vertex cover, but I mean, different flavors for different folks. Is that saying? But basically what an independent set is, you have a set of vertices, and it's an independent set if there's no edge connecting any two vertices in that set. So there's no direct connections. It's basically a disconnected set of vertices. There's no edge from any node to any other node in the independent set. Okay, let's look at some potential candidates for independent sets in this graph. Let this equal G. Well, let's put down the same ones, except I'll call them I's instead of C's. I1 equals I2 equals the empty set. Get a couple others, 4, 6, 1, sure. Four, 6, 2. Now let's come up with something else. 2, 3, 5. So these are, three examples from over here, similar ones. I4 is a little bit different, and I've left I5 blank. So I want you to take a moment, make sure you understand what's going on here. Look at this definition. Hopefully I've written it down correctly. Is an independent set if for all I, yes, correct. Look at these potential candidates of independent sets. See if they are or not, come up with an opinion, and this I5, left it blank. Come up with what you think is the largest possible independent set in this graph, okay? So pause the video, and we're back. Okay, this one, 1, 2, 3, 4, 5, 6. Is this an independent set? Well, for it to be an independent set, all of these vertices, they can't be directly connected. So let's look at 1 and 2. Oh, hold up. What? 1 and 2, they're directly connected. The edge 1, 2 is in E. It has to be that 1, 2 isn't in E. So right off the bat, boom. Not an independent set. I2? Well, it has to be true that for all vertices in here, the edge isn't in there. You check your logic rules, and for all over an empty range is going to default to the identity true, and we're in business. I2, the empty set, is an independent set. Or, yes, it is an independent set. I3, 4, 6, 1. Okay, so we have to check. 4 and 6. Is there an edge connecting 4 and 6? Nope. Okay, that's fine. What about 4 and 1? Is there an edge connecting 4 and 1? Nope. We're in business there. 6 and 1? Nope. So we're in business. That one is an independent set. What about 2, 3, 5? Well, is there an edge connecting 2 and 5? No. 2 and 3? Yeah. So immediately we know it's not an independent set. Okay. Well, what's the best independent set we could come up with? And again, I'm using best, abstractly, because before with vertex cover, best meant small. If I was looking for small independent sets, that would be a very easy problem. Why would it be an easy problem? Well, what would be the smallest independent set you could create? Right there. The empty set's an independent set. You're not going to get smaller than that, so it's a trivial problem. But when we say best, we're not looking for small with an independent set. What are we looking for? Big. Okay. What's the biggest independent set we have? Well, that's pretty big. We know we definitely can't get 6. Can we get more than 3? So I asked you guys to fill this out, and I think we can get more than 3. Let's see what we can come up with here. And hopefully I'm not giving away too much of this proof to come, but I'm just checking out some things over on this side. And you see this character here? That's not a 3. That's a bracket. Or maybe you don't see it. It's all good. Okay. What about this set of vertices? Is that an independent set? 1, 3. Are they connected? No. 1, 4. Are they connected? No. 1, 6. They aren't connected. 3 and 4 aren't connected. 3 and 6 aren't connected. 4 and 6 aren't connected. This is an independent set. And maybe I've made a dumb mistake, and there is an independent set larger than that in there, but I'm pretty confident there isn't. Pause the video, see if you can prove me wrong. I'm pretty sure you cannot. But I've been wrong many, many times in the past. So I've lost track of time here. I don't know where we're at right now. But for me, I think it's going to be a good time to take a break, see how this video turned out. Hopefully it wasn't too clunky. My apologies. Again, I didn't close the university. Not you should be blaming it people or anything else, right? But yeah, thank you very much. I'll catch you on the next lecture.